You walk into a room and forget why you went there. You read the same paragraph twice and still don't retain it. You tell yourself it's stress, but the research says something different.
Most people assume that cognitive decline is something that happens in your 70s, something gradual, something visible, something you'll notice when it becomes a problem. The research tells a completely different story. Starting around age 35, the human brain loses approximately 0.5% of its total volume every single year. That number doesn't sound dramatic until you do the math. By the time you're 50, you've lost roughly 7 to 8% of your total brain volume. By 60, it can exceed 10%. And the regions that shrink first are not random. They're the prefrontal cortex, responsible for focus, decision-making, and working memory, and the hippocampus, the structure at the center of learning and long-term memory formation. These are not the parts of the brain you can afford to lose. A 2025 study published in Nature Aging found that this volumetric decline accelerates significantly in individuals with elevated inflammatory markers, the same markers we covered in the last video. The brain doesn't shrink at a fixed rate. It shrinks faster in people with higher CRP, higher IL-6, and lower gut microbiome diversity. In other words, everything we've covered in this series feeds directly into what's happening inside your skull right now. My name is Dr. Nathan Cole. This is Hidden Health Protocol. Let's get into it.
Let me explain what's actually happening, because brain shrinkage sounds extreme, but the mechanism is surprisingly straightforward once you understand it. Your brain is made up of approximately 86 billion neurons, the cells that transmit information. But the neurons themselves are only part of the story. What's equally important is the network of connections between them, the synapses. Each neuron can have thousands of synaptic connections. The total number of synapses in a healthy adult brain is estimated at over 100 trillion. Cognitive function, your ability to think clearly, remember accurately, focus deeply, depends not just on how many neurons you have, but on how richly connected they are. After 35, two things start happening simultaneously. First, neurons begin dying at an accelerated rate, a process called neuronal atrophy. Second, the connections between surviving neurons begin to weaken and thin, a process called synaptic pruning. Both processes are normal in small amounts. Both become problematic when they accelerate. What accelerates them? Three things the research consistently points to: chronic inflammation, poor sleep, sedentary behavior, and a gut microbiome that's lost its diversity.
Here's where I want to connect the science to something you've probably already experienced, because the early signs of this decline are not dramatic, they're easy to dismiss, and most people do. The first sign is word retrieval difficulty. You're in a conversation, and the word you want is right there, and then it's not. It comes to you 30 seconds later when the moment has passed. This happens because the hippocampus, one of the first regions to show volumetric decline, plays a central role in language retrieval. When it starts to thin, word access slows before anything else does. The second sign is reduced working memory. Working memory is the mental workspace you use to hold information while you process it. Following a complex argument, keeping track of multiple variables in a decision, reading something and actually retaining it. When working memory begins to decline, tasks that used to be effortless start requiring active concentration. The third sign is slower processing speed. Your brain takes slightly longer to respond, to calculate, to decide. This isn't about intelligence. Your accumulated knowledge and reasoning remain intact. It's about the speed at which the neural signals travel between regions, and that speed is directly tied to the health of your myelin sheath, the protective coating around neurons that acts like an electrical wire. Inflammation degrades myelin. Lower myelin means slower signals. The fourth sign is what most people call brain fog, a general sense of cognitive heaviness, difficulty sustaining focus, mental fatigue that arrives earlier in the day than it used to. Brain fog is not a vague subjective complaint, it's the surface symptom of a specific set of neurobiological processes, and we're going to cover it in depth in the next video. If you've experienced any of these, and statistically, if you're watching this and you're over 35, you have, this is not a sign that something is wrong with you. It's a sign that something has been happening inside your brain that no one told you about.
Here's what changes everything about this conversation. For most of the 20th century, scientists believed that the adult brain was essentially fixed. You were born with a certain number of neurons, and from that point forward, the trajectory was only downward. Decline was considered inevitable and irreversible. That belief was wrong. In 1998, researchers at the Sahlgrenska Academy in Sweden published the first definitive evidence of neurogenesis in the adult human hippocampus, the birth of new neurons in a brain region critical to memory and learning. The finding was considered revolutionary, and the decades of research that followed confirmed it and expanded it dramatically. The adult brain is neuroplastic. It retains the ability to form new neurons, build new synaptic connections, and structurally reorganize in response to experience, behavior, and environment throughout your entire lifespan. This is not motivational language. This is neuroscience. A 2025 meta-analysis published in Neuroscience and Biobehavioral Reviews analyzed 39 controlled trials examining structural brain changes in response to aerobic exercise in adults over 40. The results were consistent. Aerobic exercise increased hippocampal volume by an average of 1 to 2%, directly reversing the shrinkage that would otherwise occur over the same period. 1 to 2% doesn't sound significant until you remember that the brain loses approximately 0.5% per year without intervention. Exercise didn't just slow the decline. In multiple studies, it reversed it. The mechanism is BDNF. Aerobic exercise is the single most potent stimulus for BDNF identified in the research. A single session of moderate-intensity cardiovascular activity increases circulating BDNF by 200 to 300% within 20 minutes, and with consistent training, baseline BDNF levels rise permanently. The fertilizer comes back, and the brain responds. Exercise is the most powerful single lever, but the research supports several additional interventions, and together they compound. First, sleep architecture. Not just sleep duration, but sleep quality. During deep sleep, specifically slow-wave sleep and REM, the brain activates a system called the glymphatic system. Think of it as the brain's overnight cleaning crew. Cerebrospinal fluid flows through the spaces between neurons, flushing out metabolic waste, including amyloid beta and tau proteins, the compounds associated with neurodegeneration. A single night of poor sleep measurably increases amyloid beta accumulation in the brain. Chronic sleep disruption accelerates the accumulation over months and years. 7 to 9 hours in a dark, cool room is not a lifestyle preference. It is a neurological maintenance requirement. Second, cognitive challenge. The brain follows the same principle as muscle: use it or lose it, but in a more specific way. Novel, effortful cognitive tasks, learning a new skill, a new language, a new instrument, drive the formation of new synaptic connections in ways that familiar, routine tasks do not. The key word is novel. Doing more of what you already do well does not produce the same structural benefit. Third, omega-3 fatty acids, specifically DHA. DHA, docosahexaenoic acid, is the primary structural fat in the brain. Approximately 60% of the brain's dry weight is fat, and DHA is its primary building block. Research consistently shows that DHA status is positively associated with brain volume, processing speed, and memory performance in adults over 40. Cold water fatty fish, salmon, sardines, and mackerel are the most concentrated dietary sources. Fourth, the gut-brain axis. Research published in Nature Microbiology confirms a direct bidirectional communication pathway between your gut microbiome and your brain, operating through the vagus nerve, through immune signaling, and through the production of neurotransmitter precursors. A healthier gut produces more serotonin precursors, more GABA, and less inflammatory signaling to the brain. Everything in the last cluster feeds directly into the cognitive outcomes in this one.
Let me bring this together. Starting around 35, your brain begins losing volume, approximately 0.5% per year in the regions most responsible for memory, focus, and processing speed. This decline is driven by neuronal atrophy, synaptic thinning, reduced BDNF, declining cerebral blood flow, and chronic inflammation. And it accelerates in people with the same risk factors we've been tracking across this entire series. The early signs are subtle: word retrieval slowing, working memory reducing, processing speed dropping, brain fog arriving earlier in the day. These are not personality traits, they are neurobiological measurements. And the research is unambiguous that the adult brain retains neuroplasticity, the capacity to grow, reorganize, and recover throughout your entire lifespan. Aerobic exercise increases hippocampal volume. Sleep allows the brain to clean itself. Novel cognitive challenge drives new connections. DHA provides the structural material the brain needs to rebuild. The decline is real, but it is not fixed, and it is not inevitable. In the next video, we're going to go deeper into brain fog specifically, what's actually happening inside the brain when it occurs, and why treating it as a symptom of stress or aging misses the underlying biology entirely. I've left a link in the description.